Right, in this section we're going to finish up Chapter 5 and look at how we can use matrices to help us with encryption. We're going to start with a couple of warm-up problems. First, suppose we want to solve the equation 4x is equal to 5 mod 7. Now remember, we don't have division in modular arithmetic, but we do sometimes have multiplicative inverses. 4 and 7 are relatively prime, which means that 4 has an inverse mod 7. And the inverse of 4 mod 7 is 2. And this is because 4 times 2 is 8, which is 1 mod 7. So what we're going to do is multiply both sides by 2. On the left side, 2 times 4x would give us 8x, but we know that's just x, right? We chose 2 because it is the inverse, the multiplicative inverse of 4. And this is 10 mod 7. Now we're just going to reduce mod 7 and get 3. If we change this problem slightly and want to solve 4x equals 5 mod 10 instead of mod 7, we run into trouble. We actually can't solve this one because 4 and 10 are not relatively prime, which means 4 has no inverse. So we can't solve this one. Because 4 has no inverse in Z10. So if I wanted to guarantee that I could always solve an equation that looks like 4x equals 5 mod n, if I want to make sure that I can always solve an equation like that, that means I want to be able to always find an inverse of something mod n, right? And in order to guarantee that all inverses exist in Zn, then the only way that happens is if all the elements of Zn are relatively prime to n. The only way that happens is if n is prime. So if I want to make sure that, if I want to guarantee that all inverses exist in Zn, then n must be prime. So our goal is to use a system of congruences to encrypt messages. We're going to associate the letters A through Z with the numbers 1 through 26. I'll let 0 be a space. So far that's 27 characters. And we need to use a prime. 27 is not prime, but 29 is the next highest prime. So let's work in Z29. That means that we need 2 more characters, and I've added in the comma and the period for 27 and 28. So we're going to use this correspondence to help us encrypt messages. In order to encrypt messages using a system of congruences, we're going to work with matrices whose entries are from Z29, right? So in the last section we just worked with matrices whose entries were from the real numbers, so we had fractions and stuff in there. But this time all of our entries are from Z29, and we're going to find that we're using matrix multiplication to do some encryption. And in order to encrypt or decrypt a message, we'll also need to be able to find the inverse of a matrix. So let's find the inverse of this matrix right here. We know the general process that we learned in the last section, and the general process holds. I'm going to set up an augmented matrix. And I'm going to put the identity next to it. I want to get the left side to look like the identity, and once I've done that, then the matrix sitting on the right side will be the inverse that I'm looking for. Now, we don't have fractions anymore, right? These aren't real numbers. We're working with entries from Z29. So if I want a 1 here, I can't multiply by a half. What I have to do is multiply by the inverse of 2. So in Z29, note that 2 inverse is equal to 15 mod 29. And that's because 2 times 15 is 30, which is 1 mod 29. So I'm going to multiply row 1 by 15 and put the result into row 1. As I do this, I'm going to reduce mod 29. Now, when I do this, I'm going to pull up a program on my calculator. You may, if you have a TI 83 or 84, you should put this program on your calculator. If you go to Canvas, there's a short video that's like less than 6 minutes long, and it will show you how to input this program onto your calculator. If you don't have that program, if you don't have the TI 83 or 84, you can use an app online like Wolfram Alpha will work. You can find inverses mod n on Wolfram Alpha. Let's multiply through each term by 15. Now, the row 2 is not being changed, so that's going to stay as is. Row 2, multiplying everything by 15. So the first one is 2 times 15, which is 30, or 1 mod 29. The way the mod program works is, and I don't necessarily need to use the program to multiply 15 by 3 and then reduce mod 29, but I'm just going to kind of show you how it works. I'm taking 15, I'm going to run the mod program. So hit PRGM. There's mod, hit enter. Now, it's going to prompt you for 2 values, A and M. So I want to multiply 15 by 3 and then reduce mod 29. So my first entry is just 15 times 3. M is your modulus, so mod 29. And we get 16. The next one, 15 times 1 is just 15. I definitely don't need the program to do that. Okay, so we got a 1 where we want it. The next goal is to get a 0 here. The way I'm going to get a 0 is to subtract 5. Now I could think of this in 2 different ways. I could think of it as subtracting 5, or since we're working in Z29, I could think of adding 24. Either will work. I'm just going to think of it as subtracting 5, and the way I get to subtract 5 is I'm going to multiply the top row by -5, add it to row 2, and put the result in row 2. Remember now, row 1 is actually not being changed in this process. Row 2 is the only row being changed. So I'm just going to write out row 1 as is. The first entry I know is going to be 0. That's how I chose this row operation. -5 times 1, 1 times -5 is -5 plus 5 is 0. So for my next entry, I want to multiply 16 by -5 and then add it to 25 and reduce mod 29. Right, so what goes here? -5 times 16 plus 25 and then reduce mod 29. We can do that right in the calculator, right in the mod program. So I'm going to enter the mod program again. -5 times 16 plus 25. I can just throw in the whole expression like that. I'm going to reduce mod 29, and I get 3. Next, -5 times 15 plus 0. So -5 times 15 plus 0, mod 29, and that's 12. -5 times 0 is 0, and 0 plus 1 is 1. So here's this entry, here's this matrix. The next thing we want is a 1 in this location. And so again, we don't have fractions, we don't have a third, but in Z29 all inverses exist. So the inverse of 3 is 10 in Z29. and that's because 3 times 10 is 30, which is 1 mod 29. So I'm going to multiply the second row by 10 and just reduce mod 29. Row 1 is not changed in this process. So 0, 10 times 3 is going to be 1, 10 times 12 is 120, and 120 mod 29 is 4, and 10 times 1 is 10, which is already reduced mod 29. Now one last thing, we want a 0 here, and the way I'm going to get a 0 is to subtract 16. I could think of it as subtracting 16, or I could think of it as adding 13. I'm just going to go ahead and write it as subtracting 16, and the way I'm going to do that is use the 1 that's below it. So I'm going to multiply row 2 by negative 16, add it to row 1, and put the result into row 1. Row 2 is not being changed in this process. So there's that row. Now to get what goes in row 1, I'm going to multiply whatever's in row 2 by negative 16 and add it to whatever's in row 1. So the first entry is a 1, right? Because negative 16 times 0 is 0, and so that leaves that entry unchanged. The next entry we know is going to be a 0. That's how I chose this operation. Negative 16 times 1 is negative 16. Add that to 16, you get 0. The last two are the ones we'll have to do a little bit of work on. Negative 16 times 4 plus 15 is what we want to do. So I'm going to use this. Negative 16 times 4 plus 15. I'm going to, enter the program again. Negative 16 times 4 plus 15. I'm going to reduce that mod 29, and we get 9. And negative 16 times 10 plus 0, mod 29 is 14. So now look, the matrix, the part on the left looks like the identity. That means that the matrix on the right is the inverse. So the inverse of the matrix 2, 3, 5, 25 is 9, 14, 4, 10. Now, if you multiply these two matrices together, remember that inverses mean that if I multiply the matrices together, I'll get that identity matrix. If we multiply these together, you'll note that you don't actually get something that looks like 1001. But when you reduce mod 29, it will be 1001. So, like these two entries, when you multiply them together, the entries in these two spots will be some multiple of 29, and the entries in these two spots will be one more than a multiple of 29. When we're doing stuff with matrices, we're going to be doing a lot of matrix multiplication to help us with the encryption and the decryption. So as I go through these next examples, you're going to see me pulling up the calculator to kind of make quick work of some of that matrix multiplication. So here's how encrypting with matrices works, where we have to choose a square matrix for encryption. So the only requirement is that it has an inverse. So we just have to make sure that one row isn't a multiple of another. If we choose a 2 by 2 matrix, that means that we encrypt our message 2 letters at a time. So if we have two plain text letters, P1 and P2, they go in this matrix here. I multiply them by that matrix, that column, by this encryption matrix, and it gives me the encrypted characters. This matrix equation here that gives us the encrypted characters is equivalent to this system of congruences. Basically, we're using a system of congruence equations to help us encrypt the messages. So when we do this, obviously C1 and C2, it doesn't pop out the letters, the encrypted text or characters right away. First it gives us the numbers, but then we're going to go back to that table on the first page of this section to go back to the characters. So we're going to use that matrix that we were just working with on the other page to encrypt a message. When we do this, we encrypt, each system of equations, right, encrypts 2 letters at a time. So you look at this and it seems like, oh, we're going to have to find this product and then this product and then this product and string them together to get our ciphertext. But you can actually encrypt the whole message in one go. You just put your plain text message in one matrix. So if I'm using a 2x2 matrix to encrypt, I just have to use like a 2x(n) matrix or to put my plain text numbers in. Just make sure that it goes in this order. You put them in column by column. Right, so P1, P2, P3, P4. Don't put them in row by row, but column by column. And then it spits out the ciphertext messages column by column. So let's say we're going to encrypt the message hello using this matrix. It's a 2x2. So we'll note that we need to encrypt in pairs. Even though we're going to do it all in one matrix, I still have to have an even number of characters. This has 5 characters, so I'm going to put in a space. I'm going to add a space so that I have an even number of characters. And what I'm going to do is, I'm just sort of chopping this up into 2-letter blocks. I'm going to go back to that table to see what numbers these correspond to. So H is 8, E is 5, L is 12, O is 15, and a space is 0. So this is 8, 5, 12, 12, 15, 0. So here's how this works. Here's my encryption matrix. In my next matrix, I'm going to put in these numbers column by column. So my first column is 8, 5. My next column is 12, 12, then 15, 0. Now we could do this by hand, but we have a calculator that will do the job. There's also a calculator app. Or like a matrix multiplication app like online that I found. So if you don't have an 83 or 84, you could use that. Just visit the calculator stuff page that's referenced on the front page to get information about that. And so on my calculator, I'm going to put in these 2 matrices. I'm going to hit the second matrix button, second matrix, and I'm going to edit some matrices. My first matrix is my encryption matrix. I need that to be a 2x2. You might already have matrices entered like I have. So I'm just going to tell it first the size, 2 rows by 2 columns. Now you can see I've got the 2x2 matrix here. And then I'm going to put in these numbers 2, 3, 5, 25. Okay, so now I'm quitting to home. I'm going to go back into my matrix menu, edit, put in my next matrix, and this was 2 rows by 3 columns. And I'm going to put in those numbers row by row, so we have 8, 12, 15, 5, 12, and 0. Now I want my calculator to multiply those matrices. This I put in matrix A, and this I put in matrix B in my calculator. So I'm going to go to the matrix menu one more time, but now I'm not editing. I'm just going to select matrix A, and then times second matrix. Now I'm going to select matrix B. There's A times B, and there's the product. So 31, 60, 30. And the second row is 165, 360, and 75. Okay. The next thing we're going to do, because these numbers don't appear anywhere on that table, right? We need to go back to characters, right? So we want to go back to that table to say, oh, okay, what letters are these? We don't have these numbers appearing at all, but we're working in Z29, so we are going to reduce mod 29. So 31, that one's easy, that's 2. And then let me call up the program. 60 mod 29 is 2. 30 mod 29 is 1. 165 mod 29 is 20. 360 mod 29 is 12, and 75 mod 29 is 17. So now I'm going to go back to the table. What letters are these? 2 is B, 20 is T, 2 is B, 12 is L, 1 is A, and 17 is Q. Okay, so what this means is that the word hello with a space translated to BTBLAQ. One thing I like to just observe about this mode of or method of encryption is it doesn't always translate one letter to the same other letter. For example, L appeared twice, and in this sequence, the LL was translated or encrypted to BL. So, that's a strength, because if you're thinking about encrypting a message, like if we know it's written in English, like a message written out in English, one thing you might do is scan for double letters showing up a lot of the time, because if you see a double letter, if every letter is always only translated to the same other letter, like if L is always a B, or if, S is always a Q or something, then when I see a double letter show up, I might think, okay, what are the double letters that often happen in English? So they'd be like L's and T's and S's and sometimes B. Like I would be able to at least say, oh, if there's a double letter, it's probably not going to be a Q. And this doesn't happen, right? So it's not that the same letter always translates to the same other letter. When we decrypt a message, we use multiplication. We multiplied by an encryption matrix to encrypt a message. So in order to decrypt a message, we're going to multiply by the inverse of that encryption matrix. So we found earlier that the inverse of the matrix 23525 is 914,410 over Z29. And so suppose somebody sent us the super secret message BTBLAQ, right? So the first thing I do is I go to that table, right, that tells me what letter corresponds to what number, and I find that this is 2, 20, 2, 12, 1, 17. And I say, okay, those are the numbers that correspond to this encrypted message. I know the decryption matrix, right? The inverse, we might call this the decryption matrix, or the decryption key. So I'm going to take this matrix, 9, 4, 14, 10, and I'm going to multiply it by the matrix. Now I'm going to put these numbers in column by column, just like we did when we encrypted a matrix. So 2, 20, 2, 12, 1, 17. I'm going to multiply. I got to enter my matrices again. So I'm going to edit. Here's a 2 by 2. 9, 14, 4, 10. And put in my other matrix, which is still a 2 by 3. So we have 2, 2, 1, 20, 12, 17. So now I'm going to take matrix A times matrix B, and I get 298, 186, 247. Now 247. And the second row, 208, 128, 174. Again, these numbers won't show up on our table anywhere, but I'm going to reduce them mod 29. So 298 mod 29 is 8. 208 mod 29 is 5. 186 mod 29 is 12. 128 mod 29 is 12. 274 mod 29 is 13. Oh, whoops, it should be 247. 247 mod 29 is 15. And 174 mod 29 is 0. Now if I go to the table, you'll see this corresponds, the first column is H, E, then L, L for the next column, then O space. So our decrypted message is hello, as we expected. Now we're reducing mod 29. I just want to point out that, like, if you just don't like the mod program, or or having a hard time making it work, you can always, if I got a number like 128 and I just want to figure out what it is mod 29 without using the mod program, I'm just going to subtract 29 and keep subtracting 29 until I get a result that's between 0 and 29, and there it is. There's 12. So that's one way you could do it. You could also do the division and then just find the remainder. But I find the mod program to be a little bit convenient and kind of bypassing some arithmetic.